I'm now going to talk about the idea of ANOVA, or analysis of variance. One of the things I'll say to start this off is that uh, if you've looked at any tutorials in Excel on regression, then what you'll note is that a lot of times you're trying to predict some outcome in a range, such as the amount of sales that are predicted by some other input that is also in a range, such as age. So income may be predicted by age, and then also maybe years of experience. This with ANOVA, at least in the examples we're going to be doing in this course, are we're trying to do predictions, but we're doing it based on differences in categories rather than differences in a range of something like age or income. So in this case, the problem that I'm looking at is we have a bookstore with books that are sold, actually a set of bookstores that are, and these bookstores sell books in the front, back, and middle of the store. And so maybe we'll say this is 7,000 sales and 12,000 sales and 10,000 sales. And across all of these stores, what we'd like to know is, do we sell more books in the front, middle, or back of the store on average? And if I charted this data right here, then it would look like this. We see that the average for front of the store sales is 9, the average for back of the store sales is 14, and the average for middle of the store sales is 11. So we might say, oh yeah, well this is, it's clear that you get more sales in the back of the store. However, that's not how things work necessarily. We know that there could be a lot of variability in the things that we're measuring, and it's possible that one single large number, for example, if I were to change this from 8 to, let's say, 28, suddenly this line changed a lot down there. Or maybe if I put in something like 50, then suddenly it changes. And so even though that's kind of an outlier there, it really changed the entire story. And so in order to determine whether there's a difference in levels of a particular factor, we call this one-way ANOVA, meaning one factor. In order to determine a difference in this, then we do a test that's called ANOVA. And there's an alternative test that we could do called a T-test. And a T-test is something we use to compare columns of data to see if they're the same or different. But that only works for 2 columns, and ANOVA actually helps us do 3 columns. So let me show you how to do it with a T-test. So with a T-test, I might say is equal T.test. And this is a little bit complicated, and you don't need to know it. But I just want to demonstrate how it works. So does the stuff in column 1 and does the stuff in column 2 differ? And if I say one-tailed distribution if I want a less conservative test, and two-tailed if I want a more conservative test, meaning it's harder to get. If I think one is higher than the other, then I would go one-tailed. If I'm not sure which one is going to be bigger, I'd say two tails. And in terms of the type of test, this is not a paired thing because it's not the same person. So in other contexts, we might have like a medical treatment, and it would be before and after the treatment. But we're not doing that. We're doing 2 samples, and we're going to assume that the data is equal in each column. If we assume that they're not, then that is again less. That's more conservative, and it's harder to get a good p-value for it. But so if I do this based on the options I just picked, it says that basically because this is less than 0.05, it's telling us that there's a pretty strong level of confidence that these two things are different. However, if I were to compare column 1 with column 3, the front and the middle, that gives me 0.10, which means we're actually not sure that those things are significantly different than one another. And if you eyeball it, that kind of makes sense. 9 is not that far off from 11, but certainly 9 and 14 looks like there's likely to be a big difference in there. Alright, now you might ask, why don't we just do a whole bunch of t-tests to see if something's bigger than another? And the reason is, I'll give kind of a poor explanation, but when we get these p-values right here, if we do this test over and over again, and so one of our answers would 0.03 and 0.003, and this one's 0.10, the chances of the the likelihood of making an error is inflated with each repeated test on the exact same data, and so we need so we might come to the wrong conclusion by doing it over and over again. At least that's what the rules tell us. So what we need is a single test that will do this without inflating our likelihood of getting an error by doing multiple t-tests. So that's why we use ANOVA. So if I go to Data, Data Analysis, I'm going to select ANOVA single factor. I'm going to grab this data right here, labels in the first row. I'm going to put my output somewhere down here. Oops, oh, that always happens, doesn't it? Okay, so my output range is going to be right there. And there's my input range. All right, now it's happy. Okay, so the output that's created here, it gives me, this is not the important part, but it gives me the averages that I've charted up there, and the amount of variability there is in each column. So if I were to think of this as kind of a bell curve, the back has a much wider bell curve than, say, for example, the middle. But the thing I'm really looking for here is this p-value. This p-value says that there is a significant difference between the levels of this single factor, and therefore we can feel confident using this for prediction. And the predictions we would use are these right here. We would predict that if you put books in the front of the stores that you're going to sell on average 9,000 or 14,000 if it's in the back of the store, or 11,000. Now that's kind of a single point estimate. In reality, we want to take into account the variability that happens, and so I'm not going to do it on this particular page, but if I might want to do something like create a confidence interval. So I might go one of these values plus or minus a margin of error, and to get that margin of error, if I wanted a 95% confidence interval, I'd take the square root of this mean squared value for within groups. If I take the square root of that, multiply that by 2, and then take that value and subtract it or add it to any of these values, that gives me a range around each of these values and about which I would say I'm 95% confident that my sales will fall in between that range. Here is another set of data that I can run an ANOVA on. I've purposely made it so this one has more variability. So in this case, you can see instead of small numbers like 1 right here, that I have very large numbers, which means that if I were to make histograms out of large numbers of observations in a column with data like this, that there's probably going to be a lot of overlap. And so if there's a lot of overlap in these columns of numbers, then it can't distinguish among the different columns of data. In other words, we're not able to confidently say that having stuff in the front, back, or middle is significantly different. In this case, because of this wide variance around each of the averages, we have a p-value that's 0.65, meaning that we can't distinguish or say with any confidence at all that putting books in the front, middle, or back makes any difference. Now here I'm not going to solve this task for you, but I did want to just kind of talk about it for a second. Here there are 4 different doctors, and we were going to ask the question, if you're treated by doctor 1, 2, 3, or 4, does that impact the number of days that you're likely to stay at a hospital? And you say that in this column it ranges from 1 to 5, in this column it ranges from, looks like 2 to 9 days, and so maybe perhaps just hypothesizing staying with Dr. 2 means being worked on by Dr. 2 means you're going to be in the hospital longer than maybe another doctor, maybe Dr. 1, since he never gets up to 9. But who knows? You have to run the analysis of variance to see what happens. Once you do that and you get an output that looks something like this, if you were to create upper and lower bounds, as I discussed previously for a confidence interval, you would take the square root of a value like this, multiply it by 2, and then add or subtract that value from whatever number is presented there for the average of front, back, or middle, and in this case it'll be for doctor 1, 2, 3, or 4. I ask you to do, so you're going to get an average for doctor 1 and an average for doctor 2. You need to calculate the square root of the within groups mean squared value. With that, multiply that by 2, subtract it from the average, and that's your lower bound, and then add it to that average, and that's your upper bound. And so you could start writing a function like equals square root of, and then go find that mean square value once you've run the analysis of variance on this particular data.